Hi, welcome to the Topology Optimization session. Here you will learn how to optimize a topology for a specific load step. You will run a model optimization for the cantilever beam from the geometry generation session and input a topology variable. This will help you to understand how you can set up the topology optimization workflow for your own products. No matter what kind of topology optimization we want to run, we always need the same four inputs, which is the constructed model. If you would like to know how to construct a FEM model that we can use for this topology optimization, have a look at the FEM analysis video, please. And then also the solid part of the design space. Also go to the same video to have a look how this is created. Then the element size of the mesh of the solid part, and then also the load step. All of these you find in the FEM analysis video. I will quickly blend them in. So this is our model. As you can see, this is the start node for the connector elements, and I use the default input, which is the center of the target geometry. So that's the same for all of us. Then this is our design space of the cantilever beam, the solid part. The element size is 1. And then we have our load step, which has a force and a fixed support. Okay, so in order for us to perform a topology optimization, we have to go through different steps. The first one is to define the topology variable. Then we will go on to define the constraint, and here we actually will have two different versions. So we will first define the constraints for a dimensioning topology optimization and then for a non-dimensioning topology optimization. The same goes for the third step, which is defining the objectives of the optimization. Again, first the objectives for a dimensioning topology optimization and then for non-dimensioning. And lastly, we will run the optimizer and have a look at the results. Before we start with our first step, I'm just going to explain real quickly why we will have those two streams, the dimensioning and non-dimensioning optimization. So the dimensioning topology optimization is ideal if we have volume AM parts, and we will get less discrete designs. And this process is ideal to be reconstructed with the quad remesher process. And then on the other hand, we have the non-dimensioning topology optimization, which will give us a very discrete design, which is ideal if you're not looking for a volume IM part, but more of a rod-shaped design, which you can then later use for the skeleton process. So you will just get the skeleton or the lines of those rod shapes and then perform a cross-section optimization. So let's get started with defining the topology variable. We have our inputs here, which is already a name for the variable. Which is given, and then we will provide the solid part. These two inputs are already sufficient for the component to run and create a topology variable, but there are many more options to define our variable. And we would like to also use the minimum and maximum diameter inputs. And I will use the element size for that. And I would like 3 times the element size as the minimum diameter. And then 6 times the element size as the maximum one. All right. And now also I would like to define a mirror symmetry plane. So if I blend in the design space, I would like the result to be symmetric to this plane, which you can see here. So I will plug in this plane into the mirror symmetry input. If you have a radial symmetric design, you can use the cyclic symmetry plane input or cyclic repetitions. And then also if you're casting a part, the draw direction is an interesting input to use. But yeah, for our application, these inputs are sufficient and we are ready to go on to our next step. In our second step, we will define which constraints our optimization needs to meet in order for a feasible result. And we will start with the first stream, the dimensioning topology optimization. So in the dimensioning topology optimization, we will optimize our part regarding the stress and displacement with constraints. And then we want to minimize the mass of the part. And as I mentioned before, the load paths of our design will not be discrete. However, a great advantage is that we can directly convert the topo result back into a solid body using the quad remesher topology reconstruction process. So we will use the stress response and the displacement response component, plug in the load step. If you want to, you can also define separate names, but yeah, because we are doing an educational example here, which is very small, it's not necessary. In a larger project, it definitely makes sense to keep an overview and defining names everywhere. Okay, so now we will use the FEM constraint component. And here I actually prepared a name because we have different constraints also for the non-dimensioning topo. And this is the response for the stress constraint. And then we have an upper bound for the stress plugged in here. And then we will use another FEM constraint component for the displacements response. And we also have an upper bound defined here. So now the optimization knows that these are the maximum values that are allowed to be reached, and if the values are exceeded, then the design is not feasible. Now we can just plug both of these into this output and are ready to take a look at the non-dimensioning topo. This topology optimization is stiffness based using the volume fraction response, and you will get very discrete load paths. However, you will need further processing because these are not dimensioned yet. So this constraint is ideal for a reconstruction process using the skeleton process. If you define those lines, these discrete lines, you get a rod-shaped result, but then you have to do a cross-section optimization to actually get the ideal result for the stress. Okay, so let's get this volume fraction response on here. We will give it a name and a model part. So our final design of the optimization will be constrained by the volume of that design. We will also use the FEM constraint component, plug in that response, give it a name, and now we will set an upper bound. So this is set to 0.1, which translates to that in the end our design is at maximum supposed to have 10% of the original volume. And if we plug this into the output, we are good to continue to the next step